Get ready for the biggest shakeup in aerospace history. Europe is challenging the status quo with a brand new strategy. Researchers at the German Aerospace Center, or DLR, have released a deep dive analysis of SpaceX's Starship performance, and they are revealing a game-changing alternative called the RLV C5. This European concept pairs a winged booster with a more efficient fuel combination, aiming to deliver over 70 tons to orbit without the massive investment needed for full reusability. We break down exactly how this partially reusable path could redefine heavy lift capabilities for the entire continent. Ambition behind this rocket. Elon Musk has reframed Starship not as a rocket, but as infrastructure designed to move over a megaton of payload to space annually. We examine the Starfactory manufacturing goals and the long-term roadmap targeting thousands of flights per year needed to sustain a civilization on Mars. Don't miss this full breakdown. Subscribe now and join the channel for the future of space. Europe is charting a potential alternative to SpaceX's Starship, focusing on a smaller, more efficient, partially reusable launch system. A recent analysis by researchers at the German Aerospace Center, DLR, has provided a detailed independent assessment of Starship's performance, moving beyond public claims to analyze raw telemetry data from initial flight tests. The Starship vehicle, a massive stainless steel rocket, has ignited a new era in spaceflight, aiming to deliver over 100 metric tons to low Earth orbit with full reusability. While the vehicle has demonstrated significant capability, the DLR study suggests its current performance is comparable to a traditional Falcon Heavy without booster recovery. However, the analysis projects that a next-generation Starship variant could achieve around 115 tons in reusable mode, potentially surpassing the Saturn V. The key finding, however, lies in the proposed European countermeasure, the RLV C5. This concept pairs the winged, reusable booster stage from DLR's Spaceliner project with an expendable upper stage, utilizing liquid hydrogen and oxygen for greater efficiency. The RLV C5 employs a unique atmospheric recovery method where the booster glides back through the atmosphere on wings before being captured by a subsonic aircraft. DLR researchers argue this approach saves propellant by eliminating the need for landing burns, maximizing the payload fraction, achieving 74% mass to orbit in useful payload, compared to only 40% for Starship. This comparison frames the development not as a direct competition, but as a strategic choice. Starship is ideal for missions demanding truly massive payloads, such as lunar bases or Mars missions. In contrast, the RLV C5 offers a path for sovereign European access to super heavy lift capabilities without the immense investment required for full reusability from scratch. DLR team acknowledges a significant gap remains. Starship's full and rapid reusability remains an unsolved engineering challenge, as evidenced by the severe damage sustained to its thermal protection system during testing. Nevertheless, the researchers conclude that the RLV C5 provides an effective route for Europe to independently develop partially reusable super heavy launch capabilities, suggesting that a smarter, more efficient path may be more critical than a purely rapid one. SpaceX is actively exploring international locations to expand the launch sites for its Starship rocket, a system designed for cargo and crew transport to Earth orbit, the Moon, and Mars. The company has indicated a strategy requiring a larger network of launch bases to achieve its goal of thousands of annual flights. In this search for viable sites, Brazil has surfaced as a potential partner, particularly due to existing agreements. This interest stems from Brazil's Technological Safeguards Agreement with the United States, which governs launches from the Alcântara Space Center in Maranhão. This treaty establishes rules to protect American technologies used in launches from that location, allowing Brazil to receive launches with U.S. origin equipment, provided specific regulations are followed. While there is no public confirmation of a formal agreement between SpaceX and the Brazilian government for using the Alcântara base, the location is frequently cited by space sector technicians as strategically advantageous, being near the equator, which can reduce fuel requirements for certain orbital missions. However, the possibility of Starship operations in Brazil is contingent upon formal negotiations, securing necessary licenses, infrastructure development, and meeting stringent legal, technical, and environmental criteria. The operational feasibility hinges on whether the geographical and legal conditions at Alcântara can support a launch of this magnitude. Meanwhile, SpaceX continues its development domestically, with test flights of the Starship Super Heavy system departing from Starbase in Boca Chica, Texas. The company is also advancing infrastructure in Florida and the United States, supporting its long-term strategy for increased launch frequency. The expansion of Starship operations globally is fundamentally tied to U.S. regulations concerning sensitive technologies, including ITAR, which necessitate host countries to provide guarantees against unauthorized access or transfer of protected technology. Other nations, including Australia, the UK, Norway, and New Zealand, have also been mentioned in international analyses regarding such safeguard agreements, with New Zealand already hosting operations for Rocket Lab. The Starship is also integral to NASA's Artemis program for lunar missions, with the vehicle selected as the system for returning astronauts to the Moon's surface. SpaceX's immediate schedule includes the 12th test flight for May 19, 2026, from Texas, which will debut version 3 of the system, featuring enhancements aimed at increasing capacity and testing features for in-orbit propellant transfer. SpaceX is preparing to launch Starship V3, positioning it as the biggest, most powerful launch vehicle ever built, with the potential to fundamentally transform the commercial spaceflight industry. Despite earlier testing setbacks, including booster explosions and engine failures, SpaceX is confident in the new iteration, targeting its first launch window for May 19. 3 key advancements highlight why Starship V3 is considered a game-changer. First, the Super Heavy booster is significantly more powerful, featuring 33 Raptor 3 engines expected to generate approximately 18 million pounds of thrust at liftoff, nearly a 10% increase over the previous generation. The upper stage also boasts 6 of these engines, producing over 3.3 million pounds of thrust. This increased thrust translates directly into vastly greater payload capacity. Starship V3 is designed to carry 100 tons to low Earth orbit, a substantial leap from Starship V2's 35 tons. This capacity increase is projected to drastically reduce the number of launches required for major missions, enabling the delivery of heavier satellites, space station modules, and lunar landers, which could ultimately lower launch costs. Second, SpaceX has implemented critical booster upgrades focused on performance and reusability. These include a redesigned fuel transfer tube for faster, simultaneous engine ignition during launch and landing, and modifications to the aft end for improved heat protection and system integration. Furthermore, the Super Heavy V3 features redesigned grid fins, 50% larger and stronger, with 3 fins instead of 4, to enhance control and precision for multiple reuses. Third, the vehicle incorporates an integrated hot staging system, replacing a single-use interstage. This design allows the upper stage engines to ignite before the booster engines are fully shut down, minimizing lost parts and post-flight repairs. Both stages are equipped with advanced avionics, integrating 60 custom units to deliver 9 megawatts of peak power. Perhaps the most transformative capability of Starship V3 is its role in enabling orbital refueling. The rocket is equipped with specialized systems, including docking drogues and propellant feed connections, designed to allow 2 starships to dock and transfer fuel in space. This capability is vital for deep space exploration, including missions to the moon and beyond, and is crucial for NASA's Artemis program, which plans to use a modified upper stage as a crew lander. SpaceX is positioned to demonstrate orbital refueling soon, a feat that promises to extend mission lifespans and further reduce launch costs. While challenges remain, a successful launch of Starship V3 could usher in a new era of spaceflight. Elon Musk has redefined the vision for Starship, positioning the vehicle not merely as a rocket, but as critical space infrastructure designed to transport over a megaton of payload to space annually. This ambitious target suggests a potential historic reduction in the cost of accessing space if achieved, requiring a simultaneous scaling of payload capacity and launch cadence. The current Starship V2 configuration carries approximately 35 metric tons to low Earth orbit. Future iterations show significant scaling. Starship V3 is projected to carry over 100 metric tons to LEO in a reusable state, with an expendable variant targeting 250 metric tons per flight. A Block 4 iteration, anticipated around 2027, aims for 200 metric tons in the reusable configuration. To achieve the megaton goal even with a 100-ton per flight capacity, SpaceX would need approximately 10,000 launches annually, equating to roughly 27 launches per day. This figure represents a long-horizon design target underpinning SpaceX's architectural decisions, rather than an immediate delivery promise. SpaceX is addressing the necessary launch cadence through the Starfactory, its manufacturing facility in South Texas, which is designed to eventually produce up to 1,000 Starships per year. Near-term goals focus on producing around 10 Super Heavy booster and Starship upper stage sets annually, with plans to expand this volume significantly. The underlying rationale for this massive scale is framed around the long-term goal of establishing a self-sustaining civilization on Mars, a logistical requirement demanding unprecedented scale. Technical advancements, such as the Raptor 3 engines, contribute to this ambition, offering substantial force improvements that directly enhance payload margins. The design philosophy centers on full reusability, high production volume, and launch rates mirroring airline operations. Near-term milestones provide grounding for this roadmap. SpaceX targets cargo flights to the lunar surface beginning in 2028 at a cost of $100 million per metric ton, with Mars cargo flights following in 2030 at the same rate. Furthermore, Starship is positioned to serve as the human landing system for NASA's Artemis IV lunar mission. Ultimately, the megaton per year target serves as the foundational specification, driving every architectural choice SpaceX has made regarding Starship's scale, reusability, and manufacturing infrastructure.